morning. Can you hear me? Everybody hear me? So there's not too many people here, but I said I would meet with you today and answer some questions. No new material. And I'll stay on until 11 o'clock. Just to solve problems or to answer questions. So the test will be at 12. And there's going to be 10 problems on the test. You have 3 hours. So that's lots of time, I hope. And I'll be on standby if you have any questions. All right, so where would you like me to go? Any particular problems you've been having? So let me emphasize that the tests are meant to be easy. I mean, I do challenge you, but they're not impossible, okay? And maybe last time you felt you didn't have enough time. So you should have more than enough time today. And okay, so you guys are writing some questions, and then yeah, it's to make you have a first attempt at solving problems under pressure in advance of the final exam, right? So that's the idea. So let's see, Nicole's asking me to look at 4.2 on, okay, so I'll open up in here. I think I can open up you guys are seeing all my sites. Okay, this is why I shouldn't have done it this way. Okay, so on En Linea, let's go here. I don't know if that's my password. Okay, good. So y'all see the page. Okay, so let's see, 4.2. 4.2. I set up the test so that you have unlimited attempts. So if you go out and go back in, you can do that until 3 o'clock. And if you even try it several times, that's fine too. Okay, it will automatically give you the result at 3 o'clock of the best score. So this one, probability can be used to interpret. Let's see if I can copy it. Can I copy it? Yes. Oh, it's a little bit. All right, let's make it. Okay, let's see. So probability can be used to interpret the results of a test. Actually, a student wrote me about this and I sent them away with details on how to do it and I never heard back. So let's see if I can get the right answer. Okay. Probability can be used to interpret the results of a test given to determine if a person is using drugs. Suppose we assume that 5% of people are drug users. So this is similar to the one we did last time. "5% of people are drug users." So I'll use the same sort of symbols that we did. So drug using, they're going to mean different things. So drug user is 5%. A test is 96% accurate, which means which we'll say means that if a person is a drug user, so that means if a person is a drug user, the result is positive 96% of the time. And if the person is not a drug user, the result is negative 96% of the time. So this is understood as sensitivity and specificity, but I'm not going to use the fancy words. Not to detract from just, that's what it is. Okay, so this is the ability to find the positives and the ability to identify negatives. Okay, that they're not, a drug user. So randomly chose. So did you get those parts? So these are the 3 pieces of information you have so far. And if the person is not a drug user, the result is, so I did all this, right? Oh, yeah, okay. Okay, a randomly chosen person tests positive. What is the probability that that person is a drug user? So now what you want to find is if a person tests positive, what's the chance that they're a drug user? So you want to invert let me move this down. All right, so you can see all of that. So this is what we want to find. We want to invert these 2 events. Should I keep going, or can you do it from here? So if I want the probability, let's see how much I have to unravel this. So I know that this is equal to the probability of let's write it like this. So I know that this is equal to the probability of testing positive and being a drug user, right? I know that that and is equal to, I can write it like this. I can write it also another way. How else can I write that? Yeah, I haven't tried this question recently, so I might, I probably should have done it before and make sure I don't go off on a wrong track, but okay. This is also the same as writing or calculating. Now this is good because I have those numbers. I have this one and I have this one, right? So what I want is this, right? So like, let's look at this again. So what I've said so far is that I can find the probability of both of them if I knew the probability of testing and I multiplied it by the probability of being a drug user given that the test is positive. So the probability of testing positive times the probability of a positive drug, to be a user when they've tested positive. That's what I want to find. I actually want to find this. But it sits in the middle of things that I know. So for instance, to calculate the green, I would have to take this one divided by this one, right? Are you with me? Tell me you're with me so far. So this is what I want. But this one resides in my understanding of them happening simultaneously. So the challenge first is to read the problem and know the difference between conditional and joint probabilities. And all kinds of probabilities. Being able to read, a problem. So this is what it says so far. Any questions about my interpretation before I continue? Or comments? So I want this. To get that, I could get this and divide by this, right? So let's see. I'm going to write that up. So I'm going to write, because everything's in red, maybe I should write it in black. I'm just going to rewrite what I have here. Now I know what this is because all I have to do is multiply these together to get it. Why don't we do that? And what do you get? I get 0.048. Okay, so that's going to be on the top. So we have the top, now we need the bottom. What's the probability of testing positive? Do I have that information? Don't have the information, I have other information. So, I could just write down Bayes' rule right now, but I'd rather unravel it for you. So, maybe you'll understand better. So what's the probability of testing positive? Well, you could be testing, a person could test positive and be a drug user, or test positive and not be a drug user. Do you agree? So by doing this, I don't know what it is to test positive, but I can break it into pieces. And this one I already know because I already calculated it. And now I need to get this. So how do I get this? Using the things that I already know. So we could rewrite, so just like I did this one, how could you rewrite this? Remember, I have things conditioned on being a drug user. So I'll write this one conditioned on being a drug user. Notice these two events are testing positive and being a drug user, that event, and the event testing positive and not being a drug user are mutually exclusive, right? So I can just add these and change my or to a plus. They don't overlap. So then, I won't write and, not to confuse you. So also, I'll say also, the probability of testing positive given, sorry, I want to write testing positive and not being a drug user can be written as, and I'm going to write it with the conditional because that's the one I know. I better write it. I'm going to make it conditioned on not being a drug user. And so now you have to think, do I have those? Do you have those values? So this is your, basically this is probably where you're missing, this is the gap in your understanding. Do you know these values? So before all this, did you follow me up until here? Any questions up until here? All right, so you don't know these values? No questions? Or no, you don't know these values. So what's this one? Does anybody identify? Can you identify what this is? Well, we know the probability that a person uses drugs. So what's the chance that they don't use drugs? So see? So this, again, you have all the skills, the tools to solve these problems. It's just that you have to do it many times in one problem, and it gets, a student sometimes doesn't realize that there's compound problems in one, and you have to solve several intermediate problems. Okay, so this is what we have to do here, but we know how to do this. Okay, so we've got that. So what's the other one? So now I have that. So I'm putting check marks that I have this one. And do I have this one? Where can I get this from? Someone tell me. So that's the chance, given you have the disease, given you aren't, I'm speaking about the other problem we did. Given that you person is not a drug user, what's the chance they have a positive test? Where do we get that information from? Where do you get it from, Nicole? Are you getting it from here? So you go to the universe where a person, the group of people who are not drug users, and the chance that their test will be negative is 96, but the chance their test will be positive will be 0.04, so you're right. So maybe this was a gap in understanding. I didn't talk about it, but anyway, we're doing it now. But that's how it works. So that means that the complement so you have to go with the given. These are the complements of each other. The one given does not use drugs. All right, so now I have that one. Okay, so let me give you a minute to put it all together and see if you get the answer. So to recap, we calculated this using this interpretation or this formula, right? This formula that I can find this two ways. I don't have this information, but I do have this information. So that's going to be 0.048. See how powerful this is? I hope I get the right answer. 0.048. And then on the bottom, it's going to be the sum of these two events. Testing positive and being a drug user, and testing positive and not being a drug user. Unfortunately, the test isn't perfect. And it allows, there's inaccuracies. And so what do we get? For the first one, we already know that's 0.048. And the second one, this amount is calculated as these two multiplied together. So let me multiply them together. This is 0.95. And that we've discussed is 0.04. So when you put those together, put that here, and then make a division. Hopefully it works. So I get 0.038. Let's see if I get the right answer. Equals 0.048. Yep. So your final answer I'll just put this number here. And when you put it all together, you get 56% or 5.8, which is the correct answer. All right? So what was possibly hard first was interpreting the problem, what you had. That just takes practice. And then knowing these complements, right? If you know this one, then you know its complement. if you know the conditional probability for not being a drug user, then you know its complement. Okay, so the condition has to be the same, and then you can do the... So the condition here has to be the same, and this is test negative, that's test positive, so those are complementary. Very good. So you only do this when you have conditional probabilities and you want to condition, two events, and you want to condition on the one you have information about to find the reverse. Okay, good. Now there was another question. Let me see the list or the chat. Okay, Gerardo's asking about different speaker. We have to get probability of picking two of the same language. Okay, I'm not sure. What's on? Anybody know which one that is? I'm gonna have a look. I guess it's in Unit 4. So it's not the first one. Not the second one. Okay, I found it. All right, let's go get it. Yeah, it's 4.3. You're right, Nicole. Okay, take a screenshot. I'm gonna pull away from this. Sorry, I was here. Okay, so let's go to 4.3. And this is it here. You should never look at the options until you're sure you've answered the question properly. Never look at the options because they are tricky. All right, Switzerland. The country of Switzerland has 3 official languages. 72% of its citizens claim German as their first language, while French is the first language of 21% of its people, and Italian is the first language of the remaining 7%. If we randomly select 2 Swiss citizens, what is the probability that they have the same first language? Okay, let me just write what I have. So I have in Switzerland, the chance of a German first language person is 72%. And French is 21%. And Italian is 7%. My good friend lives there. She speaks Italian, but English is her primary language. Interesting. Doesn't have English. Okay, so these all add up. I want to see if they add up. Right, so they add up to 100. So I guess those are the most important ones. Oh, the 3 official ones. Okay. So that's what they claim among the official languages. English is not an official language. All right, so if we randomly select 2 Swiss citizens, what is the probability that they have the same first language? Any proposals how we're going to do this? I think I have my plan. I did this years ago. I haven't looked at this for a while, but I think I have an idea of the best way to do this. So I want 2 events to happen. 2 people, right? So those are 2 incidental events. Well, the first person's outcome and the second person's outcome. So I am thinking of a matrix, right? I'm thinking about box 1, box 2. So why don't we do that? So maybe I should leave it to you. So person 1, person 2. So I'll say I feel like giving them names. So that's person 1, person 2, German, French, Italian. Now, we're picking at random, and we're making an assumption here to do this, the way I'm going to do it, that the people are chosen in a way that the outcome of the first person is independent of the outcome of the second person. So it's not like I'm not going to pick people who like live in the same household necessarily. Like, it has to be random to avoid there being an interrelationship and the people being more likely to be one or the other. So I don't like my line here. Let's make a better line. Oops. So now that you see how to do this, could you guys do this without me? Do you see where we're going? What am I looking at? Why did I do it this way? And what am I looking for? Very good, Gerardo. So the diagonal, right? I'm interested in the diagonal. So the event here is the first person's first language is German, and the second person's first language is German, which I can call G. And what is G? So let me just write this here. Probability of G and G. I'm going to assume independence of the selections. We have the people. And then you're going to multiply, because I know that I can just multiply when the events are independent, right? We talked about that. So I can just multiply those probabilities. So that's what I'm going to do all across the board here. I'm going to multiply. So I'm going to square this and put it there. I'm going to square this and put it there. And I'm going to square this and put it there. I don't have to get all of them, because all I want is the diagonal. So let's get the diagonal events. You could do this in Excel very easily. You could fill the whole table. So this one, I'm going to hold 4 decimal places. When I work with probabilities, I hold 4 decimal places. And then the other one is 0.21 equals 0.21 squared. And this one will be 0.0441, and then equals 0.07 squared. And this is 0.0049, and you have to add those together, right? Because that answers the question. What is the probability they have the same first language? And if I sum those, the answer is this. Is that the correct answer? Very good, Nicole. All right. Got it, Gerardo? So some people would have maybe gotten this because they understood. Other people might have just got it without really understanding what they were doing. But you actually use the rule of independence to do this. And knowing the probabilities, I mean, this is what you want. You want these diagonal. Okay, more questions. Any more questions? I can just stay on here. Well, I do have things to do, but if you need me, I can stay here while you study or review your notes. You want me to give you some questions? I shouldn't offer that. I've given you so many questions already. So as I said, if people came in late, there's going to be 10 questions on the test, so you should have more than enough time, but no rush. Be thorough in your answer or in your solution or solving. Pick the best option. I have a question on the other question of quiz 4.2. Okay, question 4.2. No, I don't want to go out. I just want to go to... This was 4.3. Okay. Do you have a question, or do you want me to solve this, Omar? I don't know if I can pull it over neatly. Oops, what happened to my... Oh. Back here. Suppose an individual plays a gambling game where it is possible to lose $1, break even, win $3, or win $10, and these are the probabilities for doing that. The casino's average winnings are $1.30, and the standard deviation of winnings is 3.23. After some time, the casino feels it's losing money in the long term and decides to adjust the payout levels by subtracting 1 from each prize. However, doubles the prizes so as to have a higher top prize. Alright, so what you're supposed to do is you're supposed to use the rules for mean and variances for this one. So you don't have to calculate these from scratch. So what's the rule? I have the mean already, and I have the standard deviation. And what I'm going to do is subtract. So whatever I do to the values, I also do to the mean, right? So I'm creating a new variable where I take the original and I subtract $1. I gotta be sure. So double. So subtract $1, but then double the prizes. Is it like this maybe? Does that make sense? So this would be the original winnings, right? So this variable would represent winnings. X represents winnings. And of the casino. And this is its mean, and this is its standard deviation. And then it says, subtract 1 from each prize, however, doubles the prizes so as to have a higher top prize. So let's work with this and let's see if this is the right interpretation. Okay, Gerardo, let's see if I can get another one. Another another Bayes rule problem. So basically I was applying Bayes rule, that I can use the property of what it means to be a joint probability, or this and that happening. Okay, what was I doing? So now I want to do the mean, so let's use the operator. So I write it like this to look fancy. So what does the operator do? I can write it like this, right? And for the mean, I know that the e just goes right to the x, and it does nothing to the 2. So whatever happens to the values, 2x minus 2, happens to the mean. The mean I already have as $1.30. So what is that? So that's my new mean. So this way you don't have to go back to calculating by original or by first principles, like adjusting all of these. You don't have to do that. This is the way you do it now with using the rules. Because the transformation is a linear transformation. We can do it this way. It's like it's coded. It's coded. What we call linear transformation. So what do we get? I don't think that was right. I think I have to minus 2. A 1. Let's try to do 1 from each prize, however, doubles the prizes so as to have higher top prize. I think it's going to be 2x minus 1. Makes more sense. I think it's just interpreting this. So how did you do it? You multiply, however, doubles the prizes so as to have higher top, because this is not going to give me higher. This is going to be smaller. So I will rewrite this as just 2x minus 1. Is that what you did, Omar? So double the prizes and then minus 1. So I'll just fix that. Otherwise you get 0.6 for sure. I'm not sure which one. So this is why I let you hand in your answer. So if there's debate about interpretation, for sure it's going to be 0.6, because this would have been 0.6. So let me write both of them. So if I leave it like it was before, if I do it like this, this will be 0.6. So this is just what I had before. And the reason why it's like that is because I did minus everything by 1, but then multiplied by 2. And I guess that's how you interpreted it as well. Okay. And then you're saying this is the way to interpret it. Okay. And then, oops. And then the standard deviation, remember the rule for standard deviation is just going to be whatever was in front so that's going to be the rule. So these were the rules, right, that we discussed last time. So if you multiply a variable by some number, you also multiply the standard deviation. If you add or subtract a number from the original variable, that doesn't affect the standard deviation. Shifting the distribution around doesn't affect it, but multiplying it does. Okay. And then this is the answer for the standard deviation. So you don't have to do it from scratch, Omar. You have the rules for a reason. So that's what it should be. Unless there's a typo in the answers. I'm going to put these in blue just because I'm following a color scheme. This is going to be 2 times, this is going to be 2 times 3.23, and that's equal to 646. And that's the new standard deviation. So just the rule here is from the variance. So like I do the operator here, I can use a variance operator, which is really what's going on. And that goes through this. And the variance of a sum of variables, or it just ends up, the 2 gets squared, and this one just becomes 0. Or I can write v of 2, this becomes 0. There's no variance effect on a constant. And this becomes positive, right? Because when you put the variance operator through, you square anything in front of the variable. I'm going to do this whole thing. This whole thing becomes 0. Okay. So yeah, you can do it from scratch, but then you're gonna get it wrong because it's so tedious. This avoids you getting it wrong. So all that ends up happening is that any scalar just drops out because the spread of a distribution is not affected by shifting the distribution. So that's all that happens. And to get the standard deviation, you would take the square root of this. Anyway, I'm probably writing too many symbols. It might be even confusing. But basically my point is these are the rules, right? So whatever you do to the x, you also do to the mean. Whatever you do to the x, you also do to the standard deviation, except if you're shifting, adding or subtracting. You just this drops out. If you have two variables, however, it's a little more complicated. Well, not complicated. I taught you last time how to interpret that. So okay, more problems. Oh, you want another Bayes? Another Bayes problem? I already gave you the answer to that one. There's no more in here. We just did that one, okay. You know, I probably had more and then I got rid of them because I remember having so many more. These are just basic. So you want me to make one up? That's not a good idea. I really thought I had more. I used to have them all mixed up, but no, anyway, practice assignment 4 from 2013, okay. Should we do the robbery? Question 3. Okay. A robbery has been committed, and Coco, the crime-fighting dog, has been called in to investigate. He discovers that Sonia was seen wearing gloves in the neighborhood shortly after the crime, and thus he concludes that she should be arrested. From past experience, you know that 50% of the people that Coco says should be arrested for robbery are actually guilty. Before making the arrest, you order some additional investigation. From a large population of convicted robbers, you find that 60% wore gloves at the time of the crime and continued to wear them for an interval after the crime. Further investigation reveals 80% of the people in the neighborhood of the crime were wearing gloves around the time of the crime. Okay, so what are the events of interest? Can you guys express them? What are the events of interest? In simple terms, it would be wearing gloves, I guess I'll use a G, and oh no, but then that would be wearing gloves and guilty is what I wanted to say. So I'll just say W for wearing gloves. And G for guilty. Can you guys read my writing on an iPad? Let's see if I can print it out. So W for wearing gloves. And G for guilty. So what do we know? %50 of people that Coco says should be arrested for robbery are actually guilty. Oh, but there's something else here about Coco being able to find guilty people. So we'll just say, let's see if this works. Probability of guilty equals 0.5. But no, that's Coco. Coco. Oh, guilty. Not sure. Hold on. Before making the arrest, you order some additional investigation. From a large number of convicted robbers, you find 60% wore gloves at the time of the crime and continued to wear them for an interval after the crime. Okay, so guilty people wear gloves 60% of the time. I have to be careful between the conditional and the joint probability. So probability of from robbers, right? Population of robbers. So that's like my conditional. So that's guilty. The chance that they wore gloves is 60%. Further investigation reveals that 80% of the people in the neighborhood of the crime were wearing gloves. So just wearing gloves is equal to 80%. And the only other number I have is this one here that I'm going to write as a percentage as well. So Coco says, so 50% of people that she wants arrested. I'm not sure about that one. Let me think. Okay, putting all of this information together. How would I summarize this statement? Here, the situation is that wearing gloves is 50% of the time correct that they're guilty, isn't it? No, but that's confounded with that. Let's see. So the only issue remains is, are these conditional or is this an and statement? And again, I let you submit your answers in case there's a different interpretation that we have. Okay. Okay, I'm just looking at what I wrote in the solution. So I don't contradict myself, but I don't necessarily like it. Let's see. Okay, this is an interpretation issue, okay? Let's not do this one just because it might be confusing. I'm going to interpret it differently now that I'm reading it a second time. So I'm not going to do this problem right now. The point is, however you interpret it, I will take into consideration if it's a reasonable interpretation. I'd have to look again at how I did this. And maybe I should fix the solution too to be more clear. All right, let's see the other one. There's a better one. Okay, that's the robbery. What about the next one? Cow pie computers. Is that any better? Could just be, Gerardo, it could just be that interpretation is hard. But on my tests, I do my best not to be confusing. Some of these are a little bit confusing, I guess. So let's see. Let me see if I can get the other one. I'll work that out and see if I can make it easier to understand. And let's get this one. Let's try this one if this is any better. I remember doing this, but I'm talking 8 years ago I wrote these up and I haven't really looked at them since. And a lot has happened since then. So let's see. Let's try this. If this is any better. After meeting with the regional sales manager Loretta Anderson, president of Cowpie Computers Incorporated, you find that she believes that the probability that sales will grow by 10% in the next year is 70%. So she tells you the probabilities of growth so G for growth. Yeah. Next year. Sorry, no, not 10%. The probability of growth is not 10%, it's 70%. After coming to this conclusion, she receives a report of an announcement a new operating system will be available for customers in 8 months. From past history, she knows that in situations where growth has eventually occurred, new operating systems have been announced 30% of the time. So that's easy interpretation. So where growth has occurred, that's the condition. New systems will be available 30% of the time. And then, however, in situations where growth has not eventually occurred, new operating systems have been announced 10% of the time. So they give you the opposite event. Now, it's my niece. She always calls me when I'm in class. All right, I'll call her in a bit. Am I still transmitting? Let me check. Okay. And then based on these facts, what is the probability that sales will grow by 10%? So the question is, what's the probability of growth? Given what? The facts. Okay, I have to say given the facts. Otherwise, given that you see a system. So this is the one you want, given that you see a system. So it's just the interpretation. Once you have the elements interpreted, you're on your way, I think. Are you not? So the conditional probability, I can move this around. Is always the probability of both of them divided in the subset of the event, right? So both of them happening within the subset. And then what you have to do is see what you have. Do we have this? Not exactly. Do we have this? Not exactly. So this is why we have to appeal to the full expression of Bayes' rule to expand these. S, it happens with growth or without growth, right? So S happens. So this can happen with growth and it can happen without growth. So I use that to say no growth. But I don't have those either. I don't have them either, but I can expand them using what I know about conditional for the values that I do know here. So it's just a matter of going step by step and expanding these expressions. This one, remember what and means. And means, I'll move this over. I'm trying to arrange my screen. So this and means in terms of what I know that I have the condition on growth and not growth. So let's use this one. Because that's what I'm looking for. So I'm going to say the probability of growth happening times the probability of seeing a system given growth happens. So that is how I expand this expression. And then each of these can be expanded. And then I just use my probability. So I have this, right? So all I have to do is expand these. So again, it's many levels of the same thing. So here, what's the chance of both seeing the system and there being growth at the same time? That's going to be the probability of, and again, I'm appealing to what I have here. I only have the conditions on growth. So I'm going to use it. And I have all that. And then here I'm going to expand this one. I have the condition on no growth. I can find that. I already taught you that's a complementary variable. And then systems and no growth. And you have all those numbers. So that's it. So it's just a matter of laying it out. You have this, you have this. The only one you think you don't have is this, but this is just 0.3 because it's the complement of growth. So just to be clear, the complement I don't want this, but the complement of this, you keep the condition the same, and this is the complementary event. So those would be complementary to each other, but I don't need it for what I'm doing because I'm interested in the event of a system, seeing a new system. Do you still want me to continue? I just got to put all those numbers together. So all I'm doing is using and reusing the principle that in general, the probability of two events happening is the probability of seeing A times the probability of B given A, which is also the same as the probability of B times the probability that A given B. These are the same. That property allows me to invert and find the inverted event. So all I'm doing is exploiting this relationship to the ultimate. Move this down. Okay, what does this mean again? If events were independent, and they're not necessarily, it's not necessarily the case that seeing it's not necessarily the case, right, that seeing growth is independent from seeing a system. So having seen growth, the probability of a new operating system changes. And so this is accounting for that, as opposed to just writing, just the probability of a new system every time. So I don't know, it might be interesting. So this is, let's do the calculation. Nobody's commenting. Let's make this calculation for what's the chance of a new system. That's what I need as the denominator here, and I don't have that. So I'm going to get it by finding what's the probability of a system with growth and growth at the same time, plus the probability of a system and no growth. That's going to total the probability of seeing a new system. So what is it? Let's see. That's just going to be 0.7 here times, and then here, this one is 0.3 times 0.1. So the probability of a new system this is 0.21, this is 0.03. I need to add them, so it's 0.24. So there's a 24% chance of seeing a new system, or getting a new system. And the chance of growth and a new system, I already calculated that here. That's 0.21. So the answer should be 87.5. So the chance of growth, having seen a new system with all the other information given, is quite high. Should we do some regression before I go? Or you guys have that covered? How are you for regression? Zoom out. There's nothing else. I don't know, zoom out where? Liliana. If I zoom out, I'm going to lose the image. So with this Bayes rule material, it's just a matter of practice. Don't get bogged down by the formula. I'm trying not to. I'm just using this again and again and again, and I'm trying to make that point, as opposed to writing the long formula out and then you digging up or plugging in the numbers. I did make a table in many cases so you could see all the interrelationships between the variables, or the outcomes, or what are you going to call them, the events. Are there no other questions? So for Unit 3, sorry, I'm scrolling. So understanding how to do these exercises is a good review. I hope you read through all of this. I've given you the answers as well. You're going to have to ask me a direct question because I don't know, I just don't know what you've seen. So this exercise here, Unit 3, what I do here is I make a scatter plot, find the regression line, and then make some predictions, and then I add an extra point and ask some questions about it. So here is the regression line. And it looks linear, positive, and strong. And when I look at the output, I can summarize here below that I can't highlight. But okay, it says reduction in nitrogen oxide 2 plus 0.3, I'm going to round, 2 plus 0.4 to x is basically your formula for the line. And you have an R square of 89%, very strong. 89% of the variation in nitrogen oxide is explained by the amount of additive. So this is a strong fit, it's positive, it's undebatable within the range of data. But then an extra point is acquired, and it's distal from the other points. And what this does to the line is dramatic. You can see that it really affects the line. It affects the slope, it affects the intercept, and it also affects the fit. So because of that, this new point out here in the distance is known as an influential point, and you have to be sure if you want to about what you're saying anyway. You want to be sure that this line is not really any good anymore. There's probably another shape that relates those. Oops, I want to make, no, I can't make it smaller to fit. Anyway, you can see the point. Sorry if I'm getting somebody dizzy. You can see the slope, the intercept, and the fit is affected. You can also see in the R is worse. Okay, so that point, that new observation, is considered to be influential because it does all of that. And we have to reconsider using the line. Instead, it's probably likely that a curve relationship fits, or something happens to the relationship where the additive to the solution, to the I think it's fuel, it stops having such a good effect. It becomes saturated and it doesn't do what it previously, or it could do. It's not reducing the pollutant as it was at lower amounts of additive. So you're saturating the solution and not having such a dramatic effect. So the rate of change, the rate of influence is noted by the slope dropping. The R square goes from 89, so the percent of variation being explained goes from 89% to 67%. So that's worse. So what should you do? Well, you just need to note it, and you should probably consider maybe getting a few more observations between where your range leaves off and your new observation. So this is what we did. The problem is the line is probably not good. Maybe it's better to go with something like that as a predictive relationship, as opposed to using a line. Now in this class I don't teach you how to do that, but I do have in the notes and explain how you can transform the data to get a curve relationship. So which problem is that one? Oh, number 15 in the homework, Olympic gold medal. Yeah, that one with the gold medal. Let me see. The one with the gold medal. So y hat is equal to negative 671.924 plus 0.386, all right, 56 x. And you asked, do you just plug in x? Yeah, you just use x equal 1982. Yes, so that's your, because it's, so x is year and y are the I don't know what's y again. Performance? Or the number of gold medals? Yeah. Okay. If you don't have questions, maybe I should sign off. Or I can stay here. You guys can study. And let me know if you have a question. Okay, so you guys, I can just hang out here. Let me know if you have a question. I'm not going to say anything unless you have a question for me, because I don't want to mislead you or give you anything that seems so new. Just remember, you can, if you write up the notes and you send them to me, if there's any kinds of misunderstandings or you've interpreted a problem differently, then you have the justification in your work, okay? So you can send me the work.